Hello everyone. Today I will be discussing parameterization and electric fields. How parameterization as a mathematical tool helps us with unique electric fields produced by distributed charges. My name is Adrian Gable Correa and I will be discussing this topic today. What is the logic behind parameterization? The formal definition of parameterization is it is the process of describing a system, curve, or process using independent variables called parameters, allowing for flexibility and generalization. Now, logically, since we want to simplify this, you can think of parameterization as a convenient tool that transforms our equations into different coordinate systems to make integration easier depending on the context of how our charges are arranged. Now, the equations you need to know are the following. First, you have to learn how coordinates shift from Cartesian to spherical and cylindrical. So in the first row, as you can see, this is how we could express cylindrical coordinates in terms of Cartesian coordinates or rectangular. And on the right-hand side is how we could express our rectangular coordinates in terms of cylindrical. On the bottom row, we have spherical coordinates in terms of rectangular coordinates on the left-hand side and rectangular coordinates in terms of spherical coordinates on the right-hand side. And of course, we have to remember linear charge density, surface charge density, and volume charge density. So your linear charge density is denoted with the variable with the Greek letter lambda and is defined as the distribution of charges along your unit length. Your surface charge density, denoted by sigma, is your distribution of charges per unit area. And lastly, your volume charge density is your distribution of charges per unit volume. In this case, since we're using Griffiths 4th edition or 5th edition, we're going to be denoting our differential volume with tau. So that's why you can see d tau. At this juncture, you should already be familiar with the integral form of the electric field and Gauss' law. If you're not, go back to studying. Kidding. Okay, let's go for problem 1. Okay, so for problem 1, we are to find the electric field of a distance z above one end of a straight line segment of length L that carries a uniform line charge lambda. Check that your formula is consistent with what you would expect for the case z is extremely greater than L. So in this case, for our tutorial today, we're going to be focusing more on the parameterization aspect, the application of parameterization in our electric fields, right? So we're not going to delve that deep into the integration, but we're going to show the answer, the final answer. You're going to have to do the integral yourself so that you can practice your integration as well. So we're going to start with our linear charge distribution. So we're given our linear charge density lambda, which, as you recall, is dq over dl. We can transpose dl to one side and turn it into lambda dl is equal to dq. And since we are putting our line charge along the x-axis and it's extending towards the x-axis, we could express our infinitesimal length in terms of x. So then we can just replace L with lambda dx is equal to dq. Now we have our first equation, our first variable simplified. So dq is now in terms of our linear charge density, which is already given in the problem, and is also in terms of x, which we can integrate later on. Next thing we would like to do is we would like to eliminate this variable here, this unit vector r hat. As you can recall, we could express r, any vector, as a product of its magnitude multiplied by its unit vector. So in this case, we could transpose our magnitude once again and obtain an expression for r hat, which is r vector divided by the magnitude of that said vector. And recall that in chapter 1 of Griffiths Electrodynamics that you can express your vector r as a difference of two vectors. So in this case, we could express r in terms of r minus r prime. These are still vectors, by the way, and divided by the magnitude of r minus r prime. So just a quick review. R prime is going to be the distance from your source point. Let's say this is your source point Q. So this is the source of your charges. So r prime is the distance from some origin. So in this case, we're kind of flipping the script towards spherical coordinate systems. This is going to be your r prime, which is the distance from your origin towards the source charge. And r, on the other hand, is going to be the distance from that said same origin towards your observation point. So let's say you want to find the electric field at this point. That is going to be your r. And your curly r is going to be that distance from your source charge towards the point where you're observing it. And the reason why we're going to look at it that way is so that we could make parameterization easier. So I mentioned parameterization, I think, way too much. When does the actual parameterization come in? That's a very good question. So your parameterization begins right now. So now that we have this expression for r hat, we could rewrite our integral to have all these vectors, right? Okay, we're just going to take this step by step. So from our beginning vector, let's just have it as e, right, is equal to 1 over 4 pi epsilon naught integral. We're not going to set bounds yet, but since this is a line charge, we all know that the bounds are going to be from 0 to L. Now, we already have an expression for r squared, right? Which is just going to be this magnitude. Since this is not a vector, this is more of a magnitude. So we can rewrite that in terms of magnitude. 1 over magnitude of vector r minus r prime. And that would be multiplied by your unit vector, which is basically this entire thing. We're going to write it in our equation. So r minus r prime, this is quantity squared, by the way, r minus r prime dq. We already have an expression for dq, which is just lambda delta x. Since we already have delta x, we know that we're going to be integrating our charges along the x-axis. So we could rewrite our integral and simplify things so that it doesn't look so confusing. You can bring out the lambda since it's a constant. So lambda divided by 4 pi epsilon naught integral from 0 to L all over the quantity, the magnitude of r minus r prime cubed we're now dealing with cube because these two are just essentially the same quantity. And on the numerator, we have r minus r prime dx. To look for r, we are going to look at our diagram once again. So recall the definition of r. It's the distance from your origin to your source point, to some source point. So in this case, we can write our vector r in terms of its xyz coordinates. So we're going to look at this distance over here. So from that distance, we can say that you can write it as x prime, because we're going to use prime if we're going to define distances from our origin to our source charge. Okay, so x prime 0 and 0. Why is y and z 0? Because your line charges just lie on the x-axis. Just imagine there are a lot of little small charges here. It's lying on your x-axis. Next, we need our vector. Oh wait, no, I'm sorry, pardon me, that's vector r prime. Next, we need our vector r, which is the distance from your origin to your observation point. So in this case, it lies along the z-axis. And because we're just looking at strictly on one axis, we can write r no prime as 0, 0 along z. Okay, now we have our quantities. It should practically make things easier, right? Correct. It will. Now, we simply substitute those values. So we have your electric field. We now have our lambda over 4 pi epsilon naught over here on the outside. And an integral from 0 to L. And you have your vector r minus r prime. Yet we can just, I'm going to write it over here in another color. So we have your vector r minus r prime is just going to be, so 0 minus x prime, you have negative x prime, and you have 0 minus 0 is just 0, and z minus 0 is just z. And of course, as for its magnitude, for the magnitude of r minus r prime, oops, sorry, I forgot to indicate the r prime, it's just going to be the square root of negative x prime quantity squared plus z quantity squared. Now, the next thing we would like to do is, since we now have our quantities, we could simply substitute it back in our integral. I'm going to use red so that you could see where we apply these. So on the numerator, we have your vector x prime, 0 and z. And on the denominator, we're simply going to have, okay, you know how we have cubed here, right? And this is a square root. Square root is just the power of 1/2. So we just multiply those two together, and we're essentially going to get negative, I'm just going to square it right away. So it's going to be x squared plus z squared raised to the power of 3/2 dx. Okay, cool. Now we have that. The question is, you might be a bit confused, but how do we actually solve this? Simple. You just separate it into different integrals. So remember how, vector notation, let's say x, y, z inside your brackets is just going to be x plus y plus z, right? X in the x hat, y in the y hat, z in the z hat. So you just do the same thing essentially. You could rewrite your integral to become e is equal to, we're going to just separate these into two, right? Since y is just 0, so you can have lambda, this is your first term, lambda over 4 pi epsilon naught, integral from 0 to L over, you have negative 1 over here. Yeah, I'm just gonna write it as -1. I know it's gonna be kind of confusing. I'm just gonna write it as negative x. So, but remember that this x is your distance from your origin to your source charge. So this is going to be negative x over x squared plus z squared raised to the quantity of 3/2 integrated with respect to dx. That's going to be your first term. Now your second term, I'm just going to write it down below since I'm out of space. Your second term is simply going to be lambda over 4 pi epsilon naught multiplied with z. So as you can see, your z is already outside because you're only integrating with respect to dx, which means any other variable is going to be held constant. So lambda z, just put those two together, lambda z over 4 pi epsilon naught multiplied by the integral from 0 to L of 1 over x squared plus z squared raised to the quantity of 3/2 integrated with respect to dx. That essentially is going to be your electric field expression. Problem number 2. Find the electric field at a distance z above the center of a flat circular disk of radius r that carries a uniform surface charge. From that first sentence, we now know that we have a surface charge, sigma, which, as you recall, is going to be dq over dA. What does it formally give in the limit r approaches infinity? Also check the case z is extremely greater than r. Now, from that first sentence alone, we now have an expression for dq. We can now eliminate dq. Let's put a check on that. So we can have dq is equal to sigma multiplied with our infinitesimal area. Up next, we're going to try and eliminate r hat. So we're just going to do essentially the same steps that we did for problem 1 and apply it for this problem here. So we can have E is equal to 1 over 4 pi epsilon naught integral of vector r minus r prime all over the quantity of r minus r prime squared multiplied with dq, which is essentially just sigma multiplied with our infinitesimal area. How do we look for our vector r and our vector r prime? We're going to visualize that our cylindrical disk here on our figure on the left is lying along the xy plane, right? Let's start with our vector r. Remember that vector r is the distance from your origin to your observation point. So in this case, observation point P. From the figure alone, we know that vector r is simply going to be 0, 0, and z. Next, we're going to look for vector r prime, which, as you recall, is the distance from your origin to your source charge. In this case, our source charge is this entire surface. Our not cylindrical, our circular disk is the entire source charge. So we're going to write it as x prime, y prime, and z is going to be 0 since it's lying on the floor. Now we can solve for r minus r prime. It's simply going to be negative x prime, negative y prime, and z. And as for our magnitude of r minus r prime, is simply going to be square root of x squared plus y squared plus z squared. Next, we're going to substitute those into our equation for our electric field. I'm going to bring out sigma since it's a constant at this point. Sigma over 4 pi epsilon naught integral of negative x prime, negative y prime, and z all over the quantity of x squared plus y squared plus z squared raised to the 3/2 multiplied by our infinitesimal area dA. For convenience, what we're going to do is we're going to transform this into cylindrical coordinate system. Now imagine that our figure here on the left, once again, look to your left, is a cylinder, and our disk is actually the bottom face of the cylinder. And as you can recall from our previous slides, we can express our Cartesian coordinates in terms of cylindrical. So your x becomes r cosine theta, your y becomes r sine theta, and your z remains the same. So if you think about it, polar and cylindrical coordinates are essentially the same, except that for cylindrical coordinates, you have an extra z-axis. Either way, your x and y remain the same. Now, we're going to parameterize this in terms of our cylindrical coordinate system for convenience as well when we begin to integrate. We can write it as electric field sigma over 4 pi epsilon naught with a double integral. Since we're dealing with a surface, you can tell it's a surface integral if you're integrating an area. For integrating an area, yes, you have this double integral, and we're going to change our coordinates into cylindrical coordinates. Now we can have x as negative r cosine of theta. You can have y as negative r sine of theta, and your z remains the same. As for your coordinates here at the bottom, you can have r squared cosine squared theta plus your y is going to be r squared sine squared theta plus z squared, it remains the same, raised to the power of 3/2. Now, how do we express dA in cylindrical coordinate system? Now, your dA is just going to be r differential radius multiplied by the differential theta. So think about when you integrate, you're basically integrating from the center going to your radius here, and then you go around 360 degrees so that you could form a circle. That's essentially the logic behind integrating. So you do it in one dimension, and then you go around to form a circle. That's basically what we're trying to do here. And as you can see, we could write it as r dr d theta. And then we can have our bounds. So for r, our bounds will be from 0 to capital R, which is going to be the radius of our disk. And for theta, it is going to be from 0 to 2 pi, since we are revolving around the entire circle. Now, when we begin to simplify our integral, you can notice that you could apply the trigonometric identity for the Pythagorean trigonometric identity for this. You can actually factor out r squared, and then remember that cosine squared theta plus sine squared theta is equal to 1. So then your denominator actually simplifies to sigma over 4 pi epsilon naught integral from 0 to 2 pi integral from 0 to r of negative r cosine theta negative r sine theta z all over r squared plus z squared raised to the 3 halves multiplied with r dr d theta. So as you can see, your denominator has essentially simplified even further, and you could find a form on your table of integrals that could apply to this entire integral. So as we recall, remember that we could simply split this integral into 3 separate integrals, which are easier to solve. So you can split it into an integral for negative r cosine theta multiplied with r. So when you distribute it, don't forget to, multiply the r. So you can have one surface integral for, negative r squared cosine theta all over r squared plus z squared raised to the 3 halves dr d theta. You have another surface integral for negative r squared sine theta all over r squared plus z squared raised to the 3 halves dr d theta. And your last but not the least surface integral is going to be don't forget to multiply the r over there, multiplied with r squared z squared raised to the 3 halves dr d theta. So in this case, what you're practically just integrating are your variables r squared, your variables r and theta. Now if you proceeded with dA is going to be dx, dy, and dz. Dx times dy, you could do that as well, but it's difficult to look for an integral that follows this form with two variables that you have to integrate in the denominator. It makes it difficult and annoying to solve, right? So when you parameterize and transform it for cylindrical coordinates, you're essentially looking for you can actually notice that this is an integral form for your arc sine and arc cosines. You have your r squared plus z squared form here in your integral, and you could find that on your table of integrals. So it makes it much easier to solve, and you can just cheat and use your table of integrals. At this point in physics, when you use a table of integrals, no one's gonna shame you because everybody does it.